Recording has started. Cool. So today I'm going to talk about the Linux boot process. A lot of this boot process can be applied to other operating systems, but after we cross the sort of bootloader portion of it, it's basically just going to be solely focused on Linux. Now, the core sort of reason for all of this design and all these decisions that have been made is what's called the memory hierarchy, and I've got it pulled up right here. It's essentially just sort of a rule given to us by physics and like the current process technology that we have for building computers that states that the further away the memory is from the computational device, the longer the response time. And the longer the response time, the sort of greater the storage capacity is as well. Those are kind of related factors, right? So the further away you get, the more data you can store, but the longer it takes to access that data, right? And the whole goal is to get a series of instructions right next to the logic units on the CPU that are executing those instructions, right? And those are stored in what are called registers. Then right next to the registers, you have several layers of cache, and those cache sort of allow inter-core communication and inter-core complex communication, and eventually I think there's going to be, like, as we move to a more chiplet-based architecture, you're going to have inter-chiplet communication happening as well with its own kind of cache, right? Then you have RAM, and RAM is just a much larger store, but also slower. It's still way faster than an SSD or a hard drive, but there is the main part of RAM is that it loses all of its data when you remove electricity from the system, right? Then after that, there's sort of this new middleman coming in called well, it was called Optane, but Optane's been discontinued, and it's going to come back in a different form that kind of allows it to be slotted in as RAM, but to basically become persistent storage for storing in-memory databases and stuff. And we're talking about on the size of like terabytes of space for those. Then you have your SSDs and HDDs. Those are multiple tens of terabytes. And then you have your network storage, which can be just like a ridiculous amount of hard drives, right? So we're talking hundreds of terabytes, petabytes of storage. And then you have like tape storage for like archives, like way out in another location, right? Now the operating system is usually stored on the SSD or the HDD, and we've got to load that into the registers before it can even begin executing, right? Now usually the kernel has a subsystem inside of it that is in charge of moving information up and down this memory hierarchy, from hard drive to RAM, then from RAM to cache, and then down the cache layers into the register, and then back out to RAM and back out to the hard drive. But before the system even boots, there's no kernel to be in charge of any of that moving of information up and down the memory hierarchy, so there has to be something in place that is on the board already in order to like go and fetch the kernel, right? Now, that's what's called a firmware, and you may have heard this called BIOS or Uefi, and those things are stored on CMOS chips or EEPROM chips. EEPROM just is electrically erasable read-only memory, which is kind of like a, I guess, oxymoron or whatever, but anyway, those two things are stored on chips that they don't lose their information when the machine boots, like shuts down, and when the machine turns on, that information is loaded onto the CPU and executes, right? Now I'm going to take a brief foray into electrical engineering just to sort of give you the bigger picture that there is this massive power plant that's generating just a stupid amount of electricity, right? And the way that you get that electricity from place to place is you have a voltage across a line. And the higher the voltage, the more the electricity wants to flow on that line versus going in another direction, right? So the power plant generates these massive amounts of electricity and has these huge voltage amounts to get it on the power lines to your house, right? And that voltage gets stepped down as it gets closer and closer to your house, And then eventually your house, it hits the breaker box and then steps it down even further into the 120 volt outlet that's coming out of your wall. Now the 120 volt outlet plugs into the back of your computer or to your laptop's power supply, and then that power supply feeds into a battery or just into the power supply of your computer, and that gets stepped down even further into like a 12 volt, a 6 volt, or a 3 volt rail. I think there's also a 1.5 volt rail. I'm not entirely sure, but the power supply's job in general is to take the sort of unclean power, which is this sort of like high voltage, really powerful alternating current electricity that's coming from the wall, and turn it into a very low, stable, like solid 12 volts, 6 volts, or 3 volts. That power supply then feeds those voltage rails out into the motherboard at different locations on the motherboard, and then the motherboard further steps it down into the capacitors through voltage regulators. And then the capacitors themselves store the electricity up to a certain limit, sort of like mini batteries, and then feed it into the actual chips that are doing the computation, right? And your CPU is not the only thing that's doing computation on the motherboard. There's all kinds of small little integrated circuits that are all like purposefully built to do a specific task, or are in charge of a multitude of tasks. I'm not really going to go into all that because that gets way into hardware design. But in general, you have this massive waterfall of electricity that starts at the power plant and comes down into very delicate wires that are your computer, right? And the firmware's job is to basically make sure that all that electricity is fine, right? And that all the parts on the motherboard have the appropriate power and they're working at the correct speeds, and it just checks everything, right? And that's called the POST, or the power on self-test, right? Now both the BIOS and the UEFI do that, but the UEFI offers like just a bunch of other features that I'll sort of list out in a second. But before I move on, are there any questions from you guys as far as what I just went over?
No.
I have a quick thing. So firmware, is it like a hardware thing, or is it like a software thing?
It is a software thing that is like permanently, or not really permanently, but it's required in order to make the hardware do stuff, right? Like it's sort of the most basic form of code, right, that exists on the board, right? It's the smallest code, it's the most like primitive code, right? I don't know exactly what it's programmed in, and if I'm not mistaken, UEFI implementations are largely proprietary. Both BIOS and UEFI implementations are proprietary. Let's see, if we go to, it's somewhere in here. Here it is. There's a table. So you can see that there's a couple implementations listed on the Wikipedia page, and these are sort of the different things that the BIOS is either responsible for, or the BIOS, supports things like AHCI, which is Advanced Host Controller Interface. That's how devices sort of communicate. Logical block addressing, we'll get into that in a second. Trusted Platform Module, that's for like secure boot and stuff. I'll also mention that. But these different implementations, they are built by the motherboard manufacturers for their specific board, right? And then they're loaded onto the board and stored there for whenever the machine receives electricity, right?
Wow. So is BIOS the same as firmware? Like I'm just wondering what BIOS is.
Yeah, you can kind of equate the two. So is BIOS the same as firmware? Was a question. And if essentially you can equate the two. I would say that UEFI though is more than just a firmware. It's a firmware in addition to an interface. It's literally called an interface, right? So it's this set of tools that larger programs can use to interact with the hardware as well.
Cool.
All right?
Yeah, thank you.
Cool. So once the power on self-test is done and all the other garbage is tested, and everything's working and we're ready to start executing, what we have to do is we got to find something to execute, right? And so what we're trying to find is an operating system kernel. Now, the kernel is just like the core set of tools that the operating system uses, right? So you have like scheduling software, page management, memory management, all these like individual modules that are sort of stuck together into this one, they're not all in one monolithic thing, right? But in general, they are stored as an image, right? After it's been compiled, they're stored as a single file on the disk. But the thing about that file is it's stored in a file system, right? And now a file system is a set of data structures, and let me see, where's my actual definition for it? I had here. It's a collection of data structures and the interface for reading and writing to those data structures, right? So the file system itself has a whole set of like code and instructions that we need to load into memory and execute, right? Now that's all more information that the CPU doesn't have access to the second the power button is pressed, right? Like that's not stored in the firmware. At least it wasn't stored in the BIOS, right? So UEFI came along and added all these other features, the ability to, let's see, add a list for what UEFI added. Storage. There we go. So UEFI added stuff like shell access. You can actually boot into a rudimentary UEFI shell and like run commands and traverse like the normal file systems that way. It added support for GPT. We'll talk about that later. It added the ability to do cryptography, mainly for something called Secure Boot. We'll talk about Secure Boot in a second, hopefully. It also added the ability to like move the mouse in a graphical environment on your screen instead of just like moving up, down, left, right. And then it also has backward compatibility with BIOS, right? There's a bunch of other stuff that was added as well, but in general, UEFI can boot larger amounts of information faster, and also has just a bunch of other tools for using and booting the machine, right? So I brought that up because BIOS was, so we moved away from BIOS. In general, okay, so we're looking for an operating system kernel, right? And that's stored on a file system somewhere. Now, the old way of doing stuff was BIOS plus what is called a master boot record right here. This is actually in the wrong place. I might have actually messed everything up. But universally, what is master boot? There it is. So BIOS plus a master boot record. Now, a master boot record is just a partition table. A partition table is kind of like just a glorified Excel spreadsheet that says, okay, this partition starts at this location on the hard drive and ends at this location on the hard drive, right? The hard drive is separated into 512 byte sectors, and this is where logical block addressing comes in. Basically, it just says that there are a series of blocks. Each of them is 512 bytes long, and each of these blocks has an address, right? And that's what logical block addressing is. Now, the MBR only used, let me see, that might actually be in the GPT. MBR used 32 bits to represent its addresses for each block, right? So in general, if you have 32 bits worth of objects and each object is 512 bytes long, that gives you just over 2 terabytes worth of maximal addressable storage space, right? So that means that there was no drive that you could plug in that was larger than 2 terabytes that you could fully access all of the data on the 2 terabytes if it was using the MBR partitioning scheme, right? I kind of glazed over it, but a partition is just a subsection of the drive, so we're just saying, like, I'm going to cut this drive into 4 sections, right? And I'm going to assign a name to each one. I'm going to put different information on each partition. Inside of each partition, you can store a file system, right? And the file system is, like I just said, just a group of data structures and the interface to read and write to those data structures safely, right? So after master boot record, I got to talk about GPT, or GUID partition table. It's what sort of superseded MBR, and in addition to just increasing the address space, you can see 2 to the 64 is now, or 64 bits is what is used for a single address in this partition scheme. In addition to that, the partition table can be stored anywhere on the drive, right? So if we look at master boot record, the protective MBR is just saying that the GPT system will not write to where the MBR system was writing to, just to make sure that any drives that are MBR that are plugged into a GPT system, they don't have their partition tables overwritten, nor do MBR partition tables overwrite GPT hard drives, right? So GPT starts writing after the MBR. The MBR is the first byte or the first sector on the disk. It's always the first sector. Whereas GPT can be stored sort of anywhere. It's usually started like right after the MBR, but it really can be stored anywhere on the disk, right? And the way that is enabled is through the UEFI, right? So BIOS does not support GPT. UEFI is required in order to be able to address a GPT partitioned hard drive, right? Now that might be that's a lot of like acronyms and stuff. So do you guys have that? Did that all come across?
If you don't mind, could you please repeat the GPT and the other one that you had mentioned?
MBR?
Yes.
All right, so these are different partition schemes, right? And they're just a way of saying, okay, I've got data is collected in different boxes on this hard drive, right? That's what these things are doing, right? And they're essentially saying, okay, I've got a box here that's partition 1, and it starts at address 34, and it ends at, whatever address, right? And inside that box, you don't need to know what's inside of it. All I'm telling you is that there's a box there, right? That's what these partition schemes are responsible for, right? MBR is a partition scheme that just stores at the beginning of the disk, right, all the information about what these partitions are, okay? GPT stores information somewhere else on the disk, but it also just tells you what all the partitions are, okay? Now, they both have to use address spaces, in order to tell you how many blocks a certain partition is, or basically where a block starts and where a block ends, right? I don't know if you've ever dealt with memory pointers in a program, right? You get like a little hexadecimal code that is an address, right? Just like that, these things have, each block has an address, and the address is how you access that 512 bytes of data, right? MBR uses 32 bits to represent each of its addresses, and MBR uses 64 bits, and the 64 bits times 512 bytes per address gives you about 9 zettabytes worth of data that can be addressed. Like we don't have a hard drive that's 9 zettabytes. To give you the perspective, I have the metric prefix thing here. And the biggest hard drives we have are terabytes, right? So they're right here. Your typical USB drive is like, I would say like 16 to 32 gigabytes these days, maybe 64. A typical hard drive is like at least a terabyte. A zettabyte is like way up here, right? So like three orders of magnitude larger than a terabyte is the total amount that, the total amount of data that a GPT partition table can make accessible to the UEFI. Okay. Did that help?
Absolutely, yes. Thank you.
Okay, cool. So somewhere in one of these partitions on one of these hard drives, the kernel is stored, right? And we're trying to find that kernel, right? So what we've done is, what they did with the UEFI is that they sort of standardized a file system that all of the motherboards will be able to read and write to, that will always be where you look for the kernel, essentially, right? It'll be a file system that's always readable, and it can be stored really anywhere on the disk, but that will be sort of the place where you go to find your kernel, right? And really, we're not, in some cases we're finding the kernel and booting it directly, but in a lot of other cases we're finding what's called a bootloader, right? The bootloader is kind of a leftover, but also still useful in our day and age. Let me see if I can find, I think there was an image here that really helped me out. I don't think I'll be able to find it. But in general, oh, no, here it is. It wasn't master boot record, it was BIOS. Nope. Was it just file system? No. That's not what I want to do either. Nope. Anyway, there's a sort of first level bootloader, and then a second level bootloader. The first level bootloader just goes through and finds a bootloader, and then the second level bootloader is the thing that it found, right? So a second level bootloader would be grub. I think you're used to seeing that on Linux, Rohan, but that's essentially just a thing that allows you to sort of select kernels, right, to boot from. The secondary bootloader basically gives you a UEFI kind of has a lot of the features that the second bootloader has, right? It has a shell. They both have shells. They both have the ability to boot kernels directly. They have the ability to set kernels that are automatically booted. They have the ability to navigate like rudimentary file systems and stuff, right? So there's a lot of overlap between what UEFI can do and what a secondary bootloader can do. But secondary bootloaders are still widely used for just the ability to boot multiple operating systems from a very simple list, right? And you're used to seeing that with grub, right? But there's also a refind. If I start going through the bootloaders. Ah, yeah, here it is. First stage bootloader and second stage bootloader. That's what I was talking about. And I'll have links in all these notes in the description so you can do your own reading and stuff. But in general, the main bootloader used by Linux distributions, if they use one, is grub. And I would say that, from my experience, EFI stub is the second most used bootloader. EFI stub basically just lets you program the UEFI to boot directly to this operating system instead of having to like pull up grub and like, you know, go up or down in the list, right? Followed by, I think, Refind, SysLinux, Lilo. Lilo's discontinued, but these are all Linux bootloaders that were previously in charge of navigating the file systems that are on the disk, loading them, finding the kernel on those file systems, and then loading the kernel. Right. Windows also had its own bootloader back in XP and the Server 2003 era. I'm not entirely sure what the current state is. I didn't actually get to read through the startup process for modern Windows NT. Windows NT is the name of the kernel, by the way. Right. Apple also has its own bootloader, BootX. Same kind of deal. You can see that all these operating systems, they need, because of the memory hierarchy, they need these smaller programs that can navigate the file systems, find the kernel, and then load those bigger programs, like the kernel, right? So, I guess we'll do a second break. Any questions after all that?
No, I think it's clear.
Okay.
Yeah.
All right. So after the bootloader finds the kernel is loaded. There's a lot of like, there are a couple other intermediary steps that I'm not really going to get into detail because I do want to eventually get to like systemd and all that other stuff. But in general, like there's a RAM disk that is like a prepackaged binary, right? That's sort of loaded into memory, and then that is executed, and then that finds all the other files that it needs to execute, and then those get executed, right? And you just get this hierarchy of execution that from the time you press the power button on all the way to when you see the login screen, it's just loading larger and larger and larger pieces of data, right? And that'll get compressed more and more as we move forward and as the processing technology gets better, but in general, we're still just on the road to instantaneous boot up times, right? And to be honest, that's why it's faster to just lock your phone or to just momentarily like put the computer to sleep, to have these very low power CPUs where it's always on, right? And it's always like doing just a small bit of computation, listening for when it's needed, right? And then when it's needed, it just immediately, all that stuff is already in memory, it just has to wake up, right? Instead of like going through this full on, all right, I'm awake, where's my kernel, what am I looking for? Okay, there's this device, this device, this device, this device, kernel is probably on this device, which partition is it on? It's on that partition. What file system is on that partition? Okay, I'll get the drivers for that file system and that device, and I'll read that kernel off, load it into memory. Instead of having to do that whole process, the device just stays on all the time, right? After the bootloader loads the kernel will do a whole system check in and of itself. So the kernel will inspect the CPU, figure out how many cores are on it, what's the size of the registers, what's the size of the cache, how much, what's the clock speed that it should be running at, what can it do with this CPU, right? It'll then inspect the memory, how much RAM, what's the speed that the RAM is running at, what's the latency, what's all the timings for all the individual parts of the RAM, right? How many RAM sticks, how many RAM channels, right? That kind of stuff. Then the kernel will check for device buses. Now, a bus is just a generic term that can be applied both for like software and for hardware, but in this case, the kernel is looking for an actual physical hardware bus, like PCI. I should have had that Wikipedia page pulled up, but it's kind of unanimous that like a lot of people know what PCI is, and PCI is a physical bus. It's just a wire, like a series of wires, like a very huge pipeline of wires that allows information to flow across it, right? And devices attached to this bus, and that bus leads to the CPU, or it leads to another sort of computation unit on the motherboard, and the devices communicate across that bus. It's the highway, essentially. It's a kind of highway, right? So the kernel will wake up. After checking the CPU and the memory, it'll check for all the buses, find all the buses it can, and then it'll start communicating on all those buses, trying to find out what devices are connected to those buses. So it'll like yell out and say, hey, who's here? Or those devices will already be yelling out across the bus, and the kernel will pick up those messages and start scheduling everything and setting all those devices up. So after it discovers all the devices, then it starts setting up its like scheduler, its page replacement systems, all these like more complicated algorithms that the kernel uses to like manage computation and manage control of the CPU. It sets up all that stuff, networking as well, lots of other stuff I would imagine. The kernel is a very like big piece of software, right? And then eventually it mounts all the file systems that need to be mounted, and it starts init, right? And that is the point at which what we call user space begins. Right? So in general, if you have a fast machine, all that happens in about 15 seconds. Right? I have, I'm going to get into a couple commands here, and hopefully I can can like do this relatively quickly, but I'll have to like share the entire screen for you guys. And for OBS, you already have it. So you should be able to see my terminal here, right, on Discord.
Yes.
It might be a little squished, I'm sorry. I'll try to make this as large as possible. Yeah, that text should be as large as possible, right?
Okay, so now it's much bigger.
Okay. So your main thing that actually I'll show you what I printed out as the plot for my last boot up, right? And this was, you can see, so right here you can see from the beginning of the machine's like boot up period to finally once it got into user space, we are talking at about like 36, 37 seconds, something like that. And that includes like me typing in my password and logging in and stuff, right? So the firmware boots for the first like, 1 second or whatever. Then I don't have a large bootloader right now. I'm only running Linux, so it only boots the loader. It only boots the kernel, right? So this loader is it executes really quickly, right? And then the kernel takes another 10 or something seconds, right? And then you get this thing called systemd. And I had mentioned init, but really init is just the word used to describe what's called an init system, right? Now the initial iteration of all this init stuff was something called System 5, if I'm not mistaken, or init 5, I think. And it was this sort of old way of basically just having a list of shell scripts to run. And we kind of talked about shell scripts in the first presentation, but they're just a series of sort of meta programs that can be used to run programs within them, right? They're just a series of commands to run on each shell. So an init, the init would start up, and that would start spawning processes left and right based on these shell scripts. And that, while that's good, and it got the operating system into a working state, right? What happened is after init finished its initial spawning of shell scripts and all of that running and stuff, there wasn't really infrastructure for keeping track of the shell scripts, figuring out which shell scripts required other shell scripts to run before they ran, right? There wasn't any infrastructure for this shell script spawned, but it didn't actually finish and it didn't actually complete and do what it needed to, so it failed. And this other shell script that needed it is going to try to execute, but the previous shell script failed, so that one's going to fail too, So largely over the past, I think it was 10 years, I'm not sure on the timeline of all this, but the entire Linux community and Unix as well moved to what's called an init system, or a service management sort of architecture, where you build these services, and the services are sort of started and tracked, and they all have the state of each service is sort of maintained by a single overarching system, right? And that is what systemd is, right? Now, the other options for systemd the other options to do the same thing essentially are something called Upstart, something called let's see, where do I have that? Yes, Upstart, Runit, and OpenRC. Those are the other ones that I found in my research. You'll have to do yours if you want to figure out the other ones. But in general, the majority of Linux devices out there use something called systemd, right? Now, systemd is essentially the first thing that starts in user space, right? It's the first program. It's the parent program of all the other programs, right? And it interfaces with the kernel in order to tell the hardware what to do, right? Systemd is constantly in its most ideal state, it's the one who's in charge of listening for all of the events that's happening on the computer and communicating between the kernel and user, right? So things like plugging in your USB, unplugging a USB drive, right? Things like receiving a TCP packet from the internet, right? Or a hard drive reporting an error, right? These are all events that occur sort of in a user space program that the kernel needs to be aware of, or needs to be made aware of, or another user space process needs to be aware of, right? Like, what if all of a sudden my my hard drive here just like died, right? This program that's responsible for navigating the file system, right, would have to be notified that it can't access this hard drive anymore, right? So systemd is kind of responsible for listening for events and then responding, right? And to give credit where credit's due, systemd is based on something called LaunchD, which started out, or which is a Mac OS piece of software. So Apple sort of initiated this whole deal, and that comes from the sort of architecture of the Mac OS kernel, which is heavily based on message passing. So these processes exist, and there's this common logical software bus between all of these processes that's maintained by the kernel, and the processes communicate across this bus with each other, right? And so what lognd did was it listened on this bus as well and registered all these events, and then it can, notify other processes and sort of holistically manage all of the events that the system is entering, right? It becomes a more dynamic system after you do something like systemd or lognd, or launchd, right? Whereas with the original init, it was kind of like the machine boots, it starts, it gets to like a working state, and then after that, what do, So, any questions before I get into the commands?
Yes, I think I'm clear so far.
Okay. So, I should probably... I'm going to talk about dmessage for a second. So dmessage... Oops, that's not how you spell. Dmessage. So this thing is the output from the kernel, essentially. Basically from the time that the kernel starts all the way to user space. And I don't know what the actual units here are. I don't think those are seconds. I think they're probably like microseconds. That kind of feels like microseconds. 25 seconds to get to like this final end of dmessage, right? And I can pipe that to message. Pipe that to less so that we get a little closer look at it. Right, so you can see that it's looking at a bunch of like memory addresses that it has access to. It's looking at my motherboard, what kind of motherboard I have. It checks out secure boot. Secure boot, I was gonna come back to it, but I kind of passed it up. Secure boot is just a thing that says you can only boot bootloaders that are officially like signed by the manufacturer, right? So Microsoft will have signed the Windows bootloader, and the signature will be stored on the motherboard itself. And every time the motherboard boots, it looks for a bootloader, and before it even loads that bootloader, it checks it. It like does a checksum and like cryptographically verifies that bootloader is what it's supposed to be. It hasn't been altered by some sort of like ulterior, participant or aggressor or whatever. Now, let's see, what time is it? About 4. All right, I'm going to try to wrap up relatively soon, but you can see that there's some mitigations for Spectre, right? It's kind of like the kernel's just informing of like what it's doing, what it's going through, right? Yeah, there's a lot here, but you can see that like a lot of that is happening. I don't know why I did that, but a lot of that happens like in like millisecond, right? Like this is all 0, right? This all happens like really quick, just absolutely instantaneously the second the kernel is loaded, right? So dmessage is kind of what you can look at to see if there are major issues with your kernel. There's also journal, ctl, and you can do, I think, B to get the current boot. So from here onward, to get information about the current boot. All right. Now I want to sort of draw attention. Command line right here. There's actually a better command for that, if I'm not mistaken. Yeah, cat proc. So this is the original command to like run the kernel, right? Now this is my kernel, init rd image. It says that the root is located on this drive. This UUID thing is a unique identifier to identify a specific like partition on a hard drive. There's a sort of mathematical guarantee that this number will never be sort of replicated for any other device, any other partition on this entire planet. And we use that to identify the drive, mainly because in that initial setup process, as the kernel is like looking around and trying to initialize all the things, right? It sort of initializes things in the order in which it finds them, right? So from boot to boot, there's no guarantee that it will find the device at the same time, like chronologically, as it found it the last time, right? So it may find the first hard drive first, but then the second boot, it may find the first hard drive like fifth. You know, it may find the mouse first, right? So we want to make sure that whenever we're addressing a drive, we're not addressing it with something that changes between boots, right? These are just a bunch of parameters given to the kernel, right? If the kernel doesn't know what to do with one of these parameters, it then passes it to systemd, right? And really, this is one of those. The kernel probably doesn't know how to interpret systemd.showStatus, but systemd does. And so what this does is it just says, hey, don't print anything to the screen. And if I could actually record it, I would show you that whenever my machine boots, I don't get any sort of like white text, nothing like scrolling on my screen. I just put in my password and then it takes me to the desktop. You know, the splash screen also says to like display a little like logo or whatever, right? So yeah, proc command line will tell you what the parameters that were given to your kernel are, and I will have the notes for all of this and all these stuff, so you don't have to actually memorize it. But if you also need to know a little more information, you can go to I think it's var log. What is it? And there's all these files here. These are a bunch of log files, but mainly what we're looking for is less kernel.log. Right, and this is that dmessage output, but just all in an actual file, right? That you could maybe feed to a program and do some analysis on, or like, you know, get some information about. Now the thing is that file is written to multiple times, so it'll contain information from previous boots as well. But you see, there's a bunch of log files for like all kinds of stuff, right? More than just the kernel. I will talk about systemd just in a larger capacity now. So in systemd, again, if you have a thing on Linux and you want to know what it does, you man it. And you can see this is just a giant vomit of information about what is systemd, what does it do, how do you use it, all that kind of stuff. Right? We've also got website links in the notes as well that you can check out. For the most part, trying to cite as many sources as I can. There's also a man page for the actual service that is systemd, and this has all of the different options for the service files, and I'll get into that specifically in a second. Right. So what systemd does, and I'll look at a specific service, right? So we're going to get status of ssh.service. So systemctl is the main command that you use to manage and control systemd, right? And what it does is it allows you to get basically the status of a service, or really there's a bunch of resources that systemd offers, but service is the main one I'm looking at right now. What it does is it tells you the name of the service, it gives you a description of the service, it tells you whether or not the service is loaded, so if it actually like is in the file system, right? We'll go to there in a second. Let's copy that. You can see that right now it's disabled, so that means that the next time I start this machine, the SSH service will not be started with the machine, right?
Sorry to interrupt you, Nick. I have a quick
Yeah.
question.
Yeah.
So when I type this command, if I get unit ssh.service could not be found.
That means you
This one
haven't.
in
That means you haven't installed SSH. So you'll need to do. I think. What are you on? Are you in Kali Linux?
On Ubuntu.
Ubuntu. So you'll do sudo apt install SSH. And I already SSH is already at the newest version. So you'll have to do it that way. I think one that should be on everybody's system is systemctl status network manager. Is that how you spell it? Yeah. I think network-manager.service should be one that's on your machine regardless.
Oh wow, great. I'll just try it now.
Are we a success?
Oh, great! It looks like it's working. It's showing active.
Yes. Yeah. So that's really what this sort of this printout is for, is to sort of give you the bird's eye view of the state of this service, right? So you can see Network Manager is set to be enabled whenever the system boots up. It's currently active, and it's been active here 7 hours ago. So you can tell my system uptime is probably around 7 hours. This is the process ID for the Network Manager, because it is just another process, just like everything else. This is how many tasks it has, right? How much memory it's consuming. Now the C group, I'm not going to go into C groups right now, mainly because I'm not super familiar with them quite yet, but I'm getting there. These are really, really powerful Linux kernel tools that have been used to enable everything from like Docker and containerization of basically any kind, right? Lots of virtualization stuff. They're essentially just a way to group a bunch of processes and sort of keep them isolated or separated from the rest of the system, or at the very least to manage the boundary in between those servers, those processes, and the rest of the system, right? So you can see that it started Network Manager in its own C group, right? Notice there's this thing, system.slice. I'll sort of come back to that later. I don't really know a lot about slice, but slice is another kind of systemd resource that can be used, right? Then below here, we have just a bunch of output, right? Output from what it was doing. I don't exactly know how to scroll over to the right at the moment, but yeah, you can see that there's some DHCP requests. That's how it gets an IP address, right? So I think we can do journal ctl-u network manager. Okay, so I guess it doesn't have any logs, but with journal CTL you can do the -u and then put in your service. Maybe if I add a .service, I don't think that actually changes things, but you can see all of the output related to that specific service, right? That's currently in journal CTL. I think journal CTL also just works just by itself, right? And then it has its own man page, just as everything else does. I cannot type today. Is that, I don't know how to spell journal. There we go. That looks right. So yeah, you can read up on journalctl as well. Right, here are all the possible things for you to look through. So systemd or systemctl status ssh.service. That gives you all this information. You can also stop a service. I'll have to provide my password to actually stop that service. You could also run it as sudo, but now if I run status, you can see that it's inactive. Right, I can also do systemctl status apache.service. You can see that Apache is also, Apache couldn't be found. Apache 2, there we go. You can see that Apache is currently running. So I have a web server also running, right? And you can see that there are several different processes for Apache running, and they're all in their own C group, right? Here's the process ID for the main process. Here's how much memory it's using, right? So now let's go and let's take a look at this this sort of path here. So there's lib/systemd/system. There's also etc/systemd/system. And you can see that there's just a lot of stuff in here. And what I'm really going to look at is, actually let's go, there, list that one. This has the main set of services. Etsy is, the Etsy version is supposed to be used for like system admins who are adding their own services and all that stuff. Lib is really the operating system's place. But these are all just files that we can open up and we can look at, right? So if I go here and then I grep for SSH, I'm not sure. Yeah, I should get a .ssh service or ssh.service, and then I can just look at that file. Right? Actually, I'll vim it just so we can actually kind of take a look at it. Right? So you can see description is, these are just a list of like variables, key value pairs. OpenBSD, secure shell server, documentation. These are the documents. Right after. And all of this information about like what these variables mean, what they're used for, all that stuff, stored in systemd.service. Right. See guest main PID file, remain after exit. Let's see if any of those are here. Let's look for environment file. What does that actually do? So we can search and okay, so I didn't get anything there, but you can see that exec start kind of points to something called bin/echo. And what do we know about bin/echo? Well, that's just a thing that echoes whatever you tell it to the command line, right? So this exec start thing points to a script, a shell script. It could be just another binary program, right? And then these are the options that are passed to that program, right? And this is what is executed whenever we start this service. This is what's executed whenever we reload the service, This is what we do. Under which case do we restart this service on failure? What kind of service it is? It's a notify service. So really there are different kinds of services. There are simple forking, one-shot, and notify services. Simple services just run and then they terminate whenever they're done, or they stay open, whatever. A forking service is a service that will split off and then eventually it'll keep running in the background. A one-shot service is a service that starts, moves to completion, and was needed, or it was needed by another service, and it just finishes and then it discontinues, like it stops existing, right? We don't want it to continue after that. Then a notify service is something that will run, it'll execute as much as it needs to, and then it will notify systemd whenever it's ready to receive input, right? So SSHD, or SSHD is the actual binary, right? And we can go to, what was that, user/sbin, user sbin, and we can, there it is, right there, SSHD, right? So that's an actual binary that gets executed, right? And after it's done, setting itself up and doing all this stuff, it tells systemd, yo, I'm ready for input, right? The install is the most important one. So these different sort of sections here define the different like functionality, right? Everything has a unit and an install section. This service section is solely dedicated to things that are services. Install is how you define the dependencies, right? And this will kind of be the last thing that I cover before I just sort of mention some stuff and then we'll close it out. But the dependency tree is really what brings a lot of functionality to systemd, right? And really its whole purpose is to ensure that things that have executed finish executing correctly, and things that depend on those, they don't start executing if it failed, right? So we basically want to say, don't start SSHD unless we have a user environment, right? Or unless we have reached this target, right? We don't want to even try to mount a hard drive if if mount isn't running, if the program mount is not available, which mount, it'll tell us if that binary is not available. We don't even want to try to mount a hard drive with it, right? Now those are very rudimentary examples because I've not actually had to do all this, right? Linux for the most part has set it all up for me, or Pop! OS has. But in general, there are these things called targets, and they're sort of like checkpoints that we want to reach. And in order to reach that target, all of the services associated with that target need to have succeeded. Okay? So this thing says that it is wanted by multi-user.target, which means multi-user.target will try to start SSHD, if I'm not mistaken, in its process. Right? Now, I'm going to pull up a very complicated graph here. And that's this dependency tree that you can generate too. It'll be in the description as well. But this is that way zoomed in. But you can see that there are all of these sort of nodes in the dependency tree, right? And each of these things is a systemd unit, right? And what we want to make sure is that, for instance, there's this, I can't actually tell. This is just a really small example. So cups is dependent upon SSSD service, right? I think that's it. I'm pretty sure that's exactly what that says, right? Now the green, I don't know exactly the, I don't know if there's a key here. It doesn't appear so. But there's definitely a reason why. It's definitely in the documentation for how I generated this, but you can see that there's this Init Scope, and all these different units are dependent upon each other, and the computer can use this. The systemd system, the init system, can use these dependencies to sort out what has started successfully, what has not started successfully, what can I start from here, right? And because it can do all that, it can start multiple different things simultaneously, right? And whenever something reaches a point where it can't move forward, it will just have to wait. But it can basically execute as much of the startup process in parallel as possible, while also maintaining the guarantee that all of the things will be in place whenever something needs to load and use another process, right, or another unit. Did that sort of? I know it's pretty complicated, and I'm not really super familiar with all the details of this system, right? So if that didn't come across well, just let me know. Any questions?
No, it's good from my side.
Okay, cool. So basically systemd is about where I'm going to call it. If you want to, I'll just sort of spit out a couple more commands here, just to sort of show you the cool stuff that you can do. Right. Get out here. So systemctl list-units, and you can see all the units that are currently being used, right? And I think I might actually need to run that as root. There we go. So you can see there's a bunch of mount units here. Anything with the .mount at the end is a something that mounts a hard drive or mounts a USB or something like that. These are all .device units. They all have their own sort of syntax and their own sort of key value pairs that you can use, right? I don't know why it just... Let's see if we can get to the services. There we go. So these are all services, right? MySQL service is running, network D, that kind of stuff. You can also do, list jobs. So if systemd is working on something, it's not working on anything right now, but if it's trying to start up a service or it's trying to use a resource or figure out its dependencies and stuff, it'll be a job in the systemd system, and you can see what jobs are available. You can also do -- failed to see what failed. Apparently VBox web service failed. I don't know why, but yeah. And then of course systemctl start, right? Stop, restart. What is it? Disable. All right. So if you want a service to stop running on startup, you can disable it, and if you want a service to start running on startup, you can enable it. Right. Most of the time, whenever you install a package, it will, if it's a package that is supposed to be enabled, it'll just enable itself, right? Because you sort of elevate your privileges whenever you are actually installing the package. So like SSHD, I didn't actually have to enable that service; it enabled itself, right? There's also systemctl reboot to actually reboot your machine, power off, and suspend if you wanted to. Yeah, systemd has a lot of stuff. There's a huge argument in the community over. I don't know if the argument is still happening. It probably is. There will always be soldiers who fight the fight that ended long ago, but there's this huge argument in the community about whether or not systemd is even necessary. Should it be done? Is it better than other init systems? People they like to be in charge of the change, but they don't like it when the change is in charge of them. So when things move, when the system changes and it's not what they've been a part of, then they kind of freak out and continue to fight against the tide, right? There's udevd, udev admin, but there's udevd is a thing. It's udev, right? udevd is the process that runs in the background that manages all this, but udev has been absorbed into systemd, and this thing is in charge of keeping track of all the devices that are connected to the system, right? Things like mice, keyboards, microphones, webcam, anything that connects to the system really goes through udev, and its stuff gets placed in both dev, right? All these devices created, all these device files are created by udevd. Or, yeah, udevd. Furthermore, this is actually the place where they are located. Oh. If this is, I'll show you an exact example of this, and then we'll finish up. I know I keep saying that, but there's always more to go down this rabbit hole. You know, I'm just trying to give you a full picture of as much as I can. Right. So, if I do this udev admin, right, and then I just type monitor. Do I have to run it as root? Is that the right command? Nope, it's none of that. Did I just spell it wrong? Yes, I did. Alright, so right now it's just sort of waiting, right? And if I unplug my mouse, you get a bunch of output. I can't move my mouse anymore, right? Now if I plug my mouse back in, you get another bunch of output. I'm going to go ahead and kill that. And then we can look at the output, right? So from up here, waiting on the event, then an event occurs. The mouse is unplugged from the keyboard is plugged into the computer, so it notifies the motherboard. That signal travels up the motherboard's bus across probably what I would imagine is the actual south bridge, which is another like integrated circuit on the motherboard, and that goes up into the CPU, and the CPU is notified, right? The CPU is currently running the kernel, so the kernel is also notified, and kernel runs. The kernel notifies udev, and then udev executes all these things to like unbind the files, right, and remove all these files from the system, right. Then the USB is plugged back in. The keyboard is notified of that plug-in. It notifies the motherboard. Does the same exact process. Eventually udev gets the notification, and then it adds all those files back, does some bind commands, and all that stuff, right? So if we go to this path, cd/sys/devices, you can see that there are all these different PCI buses that are available, right? And I'm specifically interested in this one. Right, so we're looking at PCI 0000/00/0000, and then we want 08 1. We go there and we list this. These are all files that describe this bus, this PCI bus number 8.1, and these are like, I could just cat max link speed. It tells me 16 giga teraflops or whatever per second, right? And cat vendor, and this is not going to make sense to me. It's just a hex value, but these are just a bunch of files that the kernel and udev. Well, really, I think the kernel writes these, and then udev reads them in order to interpret them. But you can see there's this thing called IOMMUs and IOMMU groups. We will talk about those when we get to virtualization, but those are really important as well. If we go further, we're looking for CD I think it was A, right, and then 3. If we go in here, you can see that there's a USB 3 here as well. And if I go to cat version down here at the bottom, USB 2.0, right? So literally all of the specifics about the hardware and how to access it and all of the detailed information that the kernel needs, right, becomes gets written in these files, right, on on the event that the thing is plugged in, right? And then when the thing is, unplugged, right? If I do it again, right, and I unplug it, you can see all those files get removed, right, and then re-added. Right. So this whole thing is, again, just another example of a series of small computational units called programs that are communicating with each other through this sort of intermediate interface called the kernel, right? And it's sort of just building up that larger picture that we talked about last time of, these little program creatures that it doesn't matter what computer they're running on, there will always be some sort of software interface that allows them to communicate with each other, right? So that's basically all I have. There's more notes than what I've actually covered, but in general, that's kind of all I really wanted to go over this time, for us to sort of move on to the next task. I kind of was going to talk about cron and mount specifically and all these window managers and stuff, but for the most part, that can kind of be saved for a later date. All right. Any questions? This will be the last question round.
I'm good.
Yeah?
Yeah, me too.
All right, cool. Well, if you think of some later, then don't hesitate to ask. I can, at the very least, just try to point you in the right direction, like I said, I will have all the notes and links and stuff to what I did for research, right? And I highly recommend you guys do your own research to sort of get a better idea of what's going on here, right? All right, so yeah, I'll go ahead and close it out. You guys have a phenomenal day, I hope. Stay safe out there.